Hi everyone, welcome to Ventilator Engineering. My name is Julie Lichance and I'm a PhD candidate at Princeton University in the Department of Mechanical and Aerospace Engineering. And in the past few weeks I've been leading a team of mechanical engineers and software engineers to develop a critical care ventilator in response to this COVID crisis. So I hope to put together a series of videos to share some of our knowledge with you guys in the hopes that people will create better and safer and lower cost ventilators than the one that even we come up with. We've been in touch with really supportive ICU doctors and respiratory therapists and nurses, and I hope to share some of that knowledge with you. And just generally engineering tips. I've noticed that many of the international teams have begun converging on a design, notably folks out of Milano and out of TU Delft. And I hope to provide tips that can help people who live in different parts of the world source these parts, or source parts that can work in conjunction with these designs, especially as the supply chains become even more limited than they already are. So we'll see how that goes, but for now this is just a very fundamental introductory video. I hope you learned something from it and can enter this space more quickly than you would have otherwise. So just to begin, I wanted to look at the existing DIY space. There are a ton of awesome ventilator designs out there, but I found that they generally fall into one of two broad categories. The first of which is what I call Ambubag squeezers, or BVM squeezers. And these are wonderful low-cost designs using equipment that hospitals already have on hand. And Ambubag is this blue bag shown in the MIT event design at the right. In US hospitals today, every ventilated patient will have an Ambubag at their bedside in the event of something like a power outage or ventilator malfunction. The nurse will come by and manually ventilate the patient just by squeezing this bag. The MIT event design is on the order of $100. A lot of people have made similar low-cost designs. This all-girls robotics team out of Afghanistan made a really awesome Ambubag squisher, primarily out of car parts. So a lot of great stuff in this space, but there are fundamental limitations of the Ambubag squeezer designs. Namely, doctors don't really feel comfortable leaving patients on them long term. The last I heard, typically a COVID patient needs to be on ventilator support for 2 to 3 weeks. And these Ambubags lack a lot of the fine-tuned controls that we would like for critical care patients. For example, the bags may not inflate fast enough to attain the higher breath rates required for the patients, and they typically lack things like humidification systems that we would like for patients who are fully intubated. So awesome emergency devices, maybe not so good long-term. The second broad category of ventilators are modified or improvised CPAP machines. So CPAP machines are what people with sleep apnea need to use overnight. They provide continuous positive airway pressure, CPAP, that is breathing assistance to patients who can already breathe to some extent on their own. It's a non-invasive ventilation strategy. They just have these masks that air is supplied to. And a limitation is that they pose an aerosol risk to the people in the room around them. The masks don't fully contain the particles, and so the people in the room may be infected. Nowadays, you're seeing more and more CPAP helmets that can contain some of these particulates. But in general, these devices don't attain the pressures required for those who need to be fully intubated. So if we're properly designing a critical care device, we need to do something a little more complex. So at least for my project, we're really trying to move towards a rapid deployment device using as many commercial off-the-shelf parts as possible, maybe using some 3D printed adapters. But I hope that people who are watching this video will start tackling the lower cost solution problem, looking at individual components of these designs and finding cheap alternatives to expensive parts. So good luck to you. We'll be working on that as well. Regardless of what aspect of the space you decide to tackle, I hope that safety is your top priority. You'll need to include some mechanical safety features like pressure release valves and check valves. You want to maintain a sterile air supply, and you'll also need to build some safety features into the software, including control over essential alarms. And we can talk about that in future videos as well. Likewise, I hope that you make your design pretty intuitive so that people can use it with minimal training, and make it such that it's compatible with existing tubings and fittings like the respiratory circuit in particular. If you need information about safety or compatibility with existing fittings, I encourage you to reference the ISO standards, which have recently been made available by ANSI in the United States. So you'll be able to get read-only access to these standards online, and I'll put my email in the link below if you need to reach out to get access to any standards as well. Okay, so with that, let's look at ventilator design. So really what our target is to match the breathing waveform. And this will inform a lot of the user settings that we want to give to the doctors and respiratory therapists. But fundamentally, we're going to try to match some type of pressure curve and some type of flow curve. So let's go through some of those user parameters in more detail. Okay, so the first one is the oxygen concentration, which we call FiO2, the fraction of inspired oxygen. So in medical terminology, we're talking about inspiration, that's inhaling, and expiration, that's exhaling. So this is fraction of inspired oxygen. So again, that's the oxygen concentration that can be set by fixing ratios of wall air and O2. So at least for our design, we're assuming that at the wall of the hospital, there's something like a gas blender. So I have an older medical gas blender here. It looks something like this. So normal air on its own has an oxygen concentration of 21%. And so these settings go all the way from 21% all the way up to 100. Okay? Under different settings, maybe in field hospitals, you may be working with oxygen canisters and compressed air, but for now we're assuming that we have this gas blender solution. Okay, so we also want to be able to set the pressure levels. In medical terminology, we're talking about the PIP, the peak inspiratory pressure, and that's the highest level of pressure applied to the lungs during inhalation. On this plot, that's the highest peak on that graph there. We also want to be able to maintain PEEP, that's the positive end expiratory pressure, and that's the pressure in the lungs at the end of expiration. So if you look at this plot, you'll notice that the pressure at the PEEP value is 5 cmH2O, and that's above the ambient pressure. And doctors would like to maintain the level above ambient pressure to improve gas exchange to the lungs. So we never want the lungs to fully deflate. We always want to, pop those alveoli open, I guess. We can talk more about that in future videos, but it's worth noting that you're going to need some type of controller for maintaining that lower pressure level. Additionally, we want to be able to set the breath rate, the number of breaths per minute, the tidal volume, that's the amount of gas expired per breath. So you can think about this like the lung capacity, which is typically estimated as a function of patient height in adults. And also the inspiratory time. That's the duration of inhalation. So effectively, it's the part of the duty cycle of the breath that corresponds to inhale. And you can also see this called like the I/E ratio, but effectively it's the same duty cycle consideration. And optimally, a critical care ventilator will allow for spontaneous breathing. So if the patient tries to take a breath off cycle, you should be able to do something like shift the phase to match that. And it would be ideal to run your device optionally in CPAP mode, but these are all secondary considerations. So many of the devices out there today, including commercial ventilators, sort of work on this fundamental system concept. So if we look at this schematic, we have some aspect of the device which sets the flow. Maybe it does flow limiting and pressure limiting, but it supplies a flow to a device which has a Y circuit. And from this Y circuit, there's a part of the circuit that spans to the lungs through the endotracheal tube, and another part of the circuit which is connected to an expiratory valve. So when this expiratory valve is closed and flow is supplied to the system, the lungs begin to inflate. And then when the expiratory valve is fully open, the lungs are allowed to naturally deflate as a function of the diaphragm compressing. So when you see designs out there in the world, you should be able to identify this type of fundamental circuit. If I want to break out the designs that I've been seeing in a little bit more detail, I'll come up with a block diagram that looks sort of like this. And you can feel free to pause and peruse the details of this as you see fit. But I'm going to step through this in a little more detail. So here again, at the wall of the hospital, we're looking at the existing gas supply in these green blocks. So we have the wall O2, or compressed oxygen, I guess, if you're in a field hospital setting, as well as medical air supply. And these may come natively from the wall. If so, they're supplied at 50 psi approximately, and they may go to an existing gas blender. If you don't have a gas blender, there are some pretty nice low-cost solutions involving Venturi mixers. If you have a single Venturi mixer, you can get up to 50% gas blend mixing, or you can have a dual Venturi system. But this is a nice area where people can consider lower cost solutions to existing hardware. Okay, so from the existing hospital gas supply, we enter into our device. So all the blue blocks indicate device internals. So we'll have some sort of flow controller. This may involve a proportional valve, solenoids, other types of valves. It may involve a mass flow controller, but in some sense we need a flow limiter and a pressure regulator usually. Downstream of this we have sensors as well as flow safety components. That's things like the pressure release valves if you're following a regulator. And then we move outside of the device, moving towards the respiratory circuit. So we have things like HEPA filters. If you look at my box, that's these green DAR filters to prevent contamination by the patient of the device or into the externals within the room. From the HEPA filter, we have some type of humidification system. This may be a heated humidifier or an HME. That's a heat and moisture exchanger. And then we move into the water traps to collect any condensing water to prevent pseudo-drowning of the patient. That would obviously be bad. Sensors, this sensor placement is optional. Sometimes the sensors are placed after the Y or within the device itself. And here's that Y that we mentioned. So from the Y, we can either move to the part of the circuit that goes to the patient, and there may be proximal sensors here, or we may move to the expiratory side. And again, there are water traps to prevent condensing liquid from moving through the rest of the system. There are HEPA filters to prevent contamination from the patient, as well as some expiratory sensors like flow sensors and pressure sensors, and the expiratory flow controller. So regardless of what choice of solenoid valves and proportional valves or mass flow controllers you use for these control components, most designs sort of boil down to this fundamental block diagram. You may also have extra takeoffs for emergency breathing valves to enable the patient to breathe in the event that all the valves get locked closed, but it sort of boils down to this. Okay. And okay, we have the Raspberry Pi or Arduino, some sort of system on a chip or computer powering the user I/O. That's the display with the GUI, maybe buttons and things like that to interact with the device and set the parameters. Okay, so I encourage you guys to go online, given this knowledge, and try to find pictures of commercial ventilators to see if you can identify some of those same components on the pictures that you see. So here's a random commercial ventilator that I found on the internet. And I assume that there are some flow controllers existing within the body of this device. And if I look at the respiratory circuit, I can see that this is the inspiratory side coming out of the device that moves into a heated humidification chamber. Okay, so that's a heated humidifier. And from there, we move out into some water traps. Here is a test lung or a breathing bag that's taking the place of the patient lungs at this time. And then the expiratory circuit moves back into the device where there are sensors and additional valves and things to control the flow. So it's good to look at existing commercial devices to see what you might be missing. I noticed that some of the designs out there don't take the heated humidification into account, which is very problematic because medical air is dried. And even if we were using normal compressed air, we don't want to put super dry air directly into the lungs of the patient when normally the trachea provides a lot of the moisture prior to the air entering the lungs. So it could be really damaging if we just supply direct dry air to a patient's lungs, especially if they're critically ill. So these are really worth thinking about. You want to humidify the air to 100% relative humidity at 37 degrees Celsius. Okay, awesome. Just to end off this video, I wanted to stress the point that you can get a basic working system using this sort of block diagram with relatively few components. So I've gone ahead and put together our device, taken off all the fancy components, and just set it up with 2 solenoids and a PEEP valve. So if we look at this box here, we've got the pressure regulator here at the front with the gauge, so we can set sort of an upper pressure limit, and I have 1 solenoid here and another solenoid here at the back. Likewise, we have a PEEP valve. That's just this little plastic component for setting the lower pressure value that is maintained. But I just want to stress the point that we can really inflate the bag just with effectively 2 solenoids and a PEEP valve. So here's that thing working. And I'm going to post all the GitHub code to get this device running in the description below. But I think it's really worth noting that you can get started on your design project with minimal hardware if you want to, and then extend to implementing all of the safety features that you would need if you actually wanted to use this ventilator on a patient, and that's the air compressor kicking off in your final design. But I'll leave it up to you how you implement that. Check out the existing designs on the internet, and talk to you next time.